Okay, let's do another example. This one's kind of important because, after this I'm gonna give you a homework, okay, on principal virtual work. Yeah, you've been seeing me doing this, so it'll be time for you to do it. This example is also a kind of good example to really teach you a lesson to be an engineer. What I mean is that engineer basically look at the problem and try to solve it with all that he could, and if he can figure out there's an equation or something, he'll just push forward and try to do it. So here we go. You know what I mean, but after you see this. So the problem is this. It's really rather interesting, but really, if you don't use principal virtual work, it's gonna be a pain, okay? So there is a beam. We have 40 kilonewton acting on it. Of course, not just 40 kilonewton. Then we have another distributed load on this side of the beam, that is 5 kN per meter. Okay, and it's separately supported and everything. And to make things even worse, it is kind of tied by a kind of a, I don't know what you call it, a rope, a cable, and then this cable has a length of not to scale but 5 meters. Then this cable has a cross section of 5 by 5 millimeters. And then the cross section of this guy is it's a beam, so 20 by 120 millimeters. And the location of this hanging point, this is 2 meters, 3 meters, and yeah, mid-span, 5 meters. And then we also know that this thing is made out of steel, everything. So E is 200 gigapascal, which is equals to 200 times 10 to the 9th Newton per meter square. Okay, and then yeah, we know this thing gonna somehow deforms into this shape. And we want to find out what is the delta at mid-span. Okay, just think about it. Yeah, think for a moment and then how you're going to solve it. If it's like a traditional way to do it, yeah, this is like, you're like, oh, this is so much pain. It's indeterminate. And this cable, if you give me A and length, then it's like a spring, so there's some deformation compatibility here. I'm gonna try to kind of dig this force, and I'm gonna do the compatibility and solve for everything. Oh yeah, you know what I mean. It's a pain. So how about we just do it using principal virtual work? We kind of know we're not gonna be able to find a exact solution. Yeah, if you use the traditional method of indeterminate structure and everything, then you just do that. You can find something pretty close, but we just want to get this delta. So what do we do? And so let's see if we can be clever and figure out how we want to do this. Vx. Okay, let's say this is y and this is x. We know this thing is like a curve got a 0 at x equals 0, got a 0 at x equals to 10, and the maximum probably here, I don't know, let's just assume it's here. So what do you guys think? In fact, yeah, we're just gonna do it the simple way. We just say it's delta and times sine pi over 10x. Okay, yeah, this thing works. So if you put x equals 0, sine 0 is 0. If you put x equals 10, sine pi is 0. And when you do this, now we're working with the real numbers. You need to give this a unit. You need to say, okay, this is probably in meters. But then someone's gonna immediately come back to me and say, hey, this is not correct. You know what? Because this guy is symmetric, what you assumed. But it looks like this thing not gonna be symmetric. There's gonna be some wobbling thing here. Yeah. I mean, it'll actually do something like this. But let me tell you, like, how can you find a function that will actually do this, and in a simple way? We'll say this is, good enough, so we're gonna go with this. Under this assumption, we're gonna derive principal virtual work, and then they're gonna give us a number here, eventually, when we plug everything in. So, as a rule of thumb, you got this, then you just delta sine pi over 10x. Okay, this is also in meter, but in fact, you know what, this actually doesn't matter, because this is just a factor, and this can be anything, so yeah, whatever. And this gonna go off anyway. So you get that taken care of. The beauty is that now not only you know every single point, how much they moved on the beam, you also know how much this guy extend. The extension on this cable is simply, if you plug in x equals to 2, you're gonna get it. Okay, that means we will also know the deformation stress and strain inside this cable now. So now let's do the principle of virtual work, which is basically not equals to, but basically saying that external work equals to internal work. External work will be the work done by the external forces. So how do you do that? Let's do that first. Right now there's like two things that do it. The first one is the 40 times when the virtual displacement at the mid-span, which is, you plug in 5 here, so half of pi, sine half of pi is just 1. Sine 90 degrees is 1, okay? So it's just this. Then also this downward distributed force also will do work, and then we already know from last class it's 0 to 5, and then the 5 kN per minute, this is our Q, and then do this displacement function, which is virtual. Yep. Oh boy, I hope you guys still remember how to do something like this. The way to do it is actually to do a transformation. So basically you rewrite this 40 this plus first of all, the delta and the 5, you can take it out because that's a constant, nothing fancy about that. And then you do a 5 0, and then you kind of do a little trick, sine pi 10x. Then you do the d pi 10x. You added this thing here to, in order to make this everything work, you need to do the 10 over pi here. So those two guys, they kind of cancel each other. It's like you have done nothing. But then if you look at this guy, you call it t, and then this guy you call it t, Then this part specifically can be written like this part. Can be written as, you take this guy out, 50 over pi. And then you change your integral limits and using the t, because 0 to 5 for x is really 0 to pi over 2 for t, sine t dt. And we all know the integral of sine t is actually negative cosine t. So this part specifically is actually negative cosine t evaluated at pi over 2 and 0, which equals to negative cosine pi over 2, which is 0, minus negative cosine 0, which is 1, but there's minus, so it's actually just 1. So after all that, then you say, okay, external virtual work actually just equals to this guy, 40 plus 50 over pi. Yeah, that's it. And then, did I talk about unit thing? I did 40, but it's 40 kn, right? If you're ever confusing about units, just change everything into a base unit. So what I'm going to do here, because I know that the delta here, I said it's meter, okay? Let's just do meter Newton. So I'm just going to do 10 to the third, and then I actually say this is Newton meter. So there's no confusion. Okay, now the internal virtual work, that's a fun part. Okay, is something like this. Internal is the you need to ask yourself. You're looking at the entire system. Anything deforms, they have real stress in them. And then if your virtual displacement gonna induce some virtual strain in those components, they will all do virtual work. So in this specific example, you have the virtual work coming from the deformation of the beam, and you also have the virtual work internally from this string or bar or whatever you want to call it. To do it, the formula for the beam is EI 0 over 10, and then we got your dV is dx second derivative, d virtual v dx second derivative, and then dx. Okay. Then the bar here, basically just by our understanding, or the very fundamental thing is basically we know there's only axial force in there, so it's the integral over the volume of the actual stress in the bar times the virtual strain in the bar, and then we'll integrate over the volume. But then you're like, hey, how am I gonna do this? You never told me how to do that. Okay, here's the engineering thing come along. We solve problems step by step. So first you need to realize that, like, this guy and this guy inside that bar, they are all constant inside the bar. If they're constant, and then you're doing integral over the volume, this part simply is just the volume times the constants. So you got the volume is A times L, okay? That's the volume. And then just times the constant bar stress times the constant bar virtual strain. And then we also know that the E, right? So we can further do this as A, E, L. Then this, because you divide by E, it is the real string in the bar and virtual string in the bar. And then you're like, okay, what are those? Those are normal strings. So in fact, if you want to move forward, this guy is actually just the real delta L over L. This guy is actually the virtual delta L over L. And then you're like, okay, what is that? Yeah, didn't we say that if we know the virtual displacement, then all we need to do, see how much this delta is just to plug 2 into here. So what came down to is that this term is actually delta sine pi over 5 over L, and then this guy is delta sine pi over 5 L. Yeah, because the virtual displacement and the real displacement, they are having the same format. The only difference is that this delta is the real, this guy is virtual. So if you consider all these and then come back to here, you find out that this integral is simply equals to A E over L and then sine pi over 5 squared times delta times delta. Wow, okay, that you're like, okay, that's pretty cool. Then we take care of this part. Then how about this guy? This guy's actually quite simple. Yeah, if we're in class, I'm gonna ask you what's the second derivative of sine. Everybody knows it's actually a negative sign because simply you do sine, then you go to cosine, then you cosine, you do another derivative, you get back, then you have a negative. But here there's a little bit more because the x is not just x, it's like pi over 10x. So every time you do sine, you do derivative, you actually take this out twice, so it becomes squared. Long story short, what you're gonna get is something like this. And of course, at the same time, you like delta and delta, they are constant, so they don't change, so they can come out. So in the end, what you get is something kind of interesting like this. It's E I, that's already there. You got delta and delta, they just constant, they come out. And then you got a pi fourth, 10 to the fourth. That's because, the pi and tenths, the second derivative, they'll come out. They'll come out to be second, and then you have two of them, you get fourth. Then finally, you got the 0 to 10, and then you have this sine square. Yep, that's it. Okay, so you're like, okay, how am I gonna do this? In fact, when I do this, I was like, I don't know. So, but that's the thing about engineers, coming in. As an engineer, you're not a mathematician, okay? You're not supposed to remember all that type of stuff. What you need to know as an engineer is that there is a solution that I can find somewhere, and then I know how to find it. So in a way, it's actually, I just Googled it up, but you might have some other fancy ways, but as an engineer, you just need to know the problem and know where the solution is. The details about solution, what formula to use and all that, yeah, that's actually not that important for an engineer. Okay, so anyway, let's get this components out of the way. E, I, delta, little delta, pi force, 10 force, and then we'll do the same trick. So 0 to 10 sine pi 10x squared. Then we'll do a pi under 10. Then we'll do a d 10 pi x. And then we're gonna do the same trick. Make this t. And then, of course, this guy came out. This guy came out, and in fact, just cancel out one of those. So you got ei delta delta pi third and 10 third. And then the t, it will be from 0. If you put 10 to x, you find out, you find out that for t is actually 0 to pi sine t squared dt. This is a kind of a classic thing. Yeah, just a note. If you have an integral of sine square x dx, that one is actually equals to x over 2 minus sine 2x over 4 plus c. But anyway, we're gonna get rid of that because we're definite integral. So you do that, you find out what you have is t over 2 minus sine 2t over 4 evaluated from 0 to pi. If you put 0 in there, everything's 0. Okay, so you just put in pi in there. Put pi in there is 2 pi over 2. This guy is sine 2 pi. Sine 2 pi is, 0. So it's actually pi over 2. So this entire thing is actually pi over 2. Okay, so let's like combine this information and also the information over there. You find out the internal work in the end actually equals to if you you see, like here you have E, you have delta, and here you have E, you have delta and delta, so they are actually the same. So you get like E delta delta, you can take that out, and what you end up with is I times pi to the 4th, and then 2 times 10 to the 3rd. That's actually this chunk, the internal work for the beams. Then plus whatever is coming out from here, which is A divided by L times sine pi over 5 squared. That's it. That's your internal virtual work. So now we apply the principle of virtual work. We'll make this guy has to equals to this guy, and then the delta can be anything. So you have an equation of this guy actually equals to all those bunch of stuff, but then you can solve for delta. So let's do it. I'm gonna this is the internal, and then I'm gonna say it's equals to the external. I'm gonna copy it. It's delta 40 plus 50 over pi times 10 to the 3rd. Oh yeah, then you're like, wait a second. This one is we know it's external, and it is a Newton meter. How about the unit for this one? The unit for this one, depending on what kind of unit you put in, because like a sine pi, this, and delta, it doesn't really matter. So if you think delta is gonna be in meter, you just need to make sure do this in meter, Newton, do everything like A in meter, this guy in meter, I in meter, then you'll be fine. So make sure you do that. Okay, then you're like, okay, that's all cool, but can you do it? Yeah, for this problem, I'm just actually gonna do it. So what you need to do is let me rewrite this. So basically, we're gonna get rid of this. Then we're gonna get delta. We're gonna actually solve for delta, right? So you can just write delta equals to so basically this whole thing divided by whatever this is, and E. So you got 40 plus 50 divided by pi times 10 to the third divided by a whole bunch of stuff. First one is E, and then you got this I pi fourth over 2 times 10 to the third, then plus this a sine pi over 5 squared divided by L. That's it. Okay, so let's do some calculation, and then I'll say you get your calculator out, but yeah, you don't have it. I got it. So what happens is that yeah, first of all, you calculate this. I mean, it's easy to calculate. The number is actually 55.915, and then times 10 to the third. Okay, that's easy enough. Then it comes E. Okay, now here's the thing. Here's what we know, right? The E is 200 thing, and then like here, it's already giving us in Newton meter, so we just go ahead and use that. So you got 200 times, you're gonna do 10 to the 9th. Yeah, no, you know what? I'm gonna do 10 to the 6th. I'm gonna get rid of this. Oh, that's fine. Then inside it, you got I. Okay, what's the I here? The I should be 12 over BH third, right? So if you plug everything in, it's 12 over 20 times 1/20th third. But remember, if you do that, that's millimeter force. So yeah, that's no problem. You go ahead and calculate it. This actually turned out to be 2.88 times 10 to the 6. But this number, then to change that back to meter, because 1 meter or 1 millimeter is like a third of power, and then you have a force, so it's times 10 to the negative 12th. Then that'll give it into meter force. So let's just do that. So it turns out to be that guy is actually 2.88 times 10 to the negative 6 because of that conversion. And then pi force, and then do the 2 times 10 to the third. Okay. Now the A here, 5 by 5 millimeter, so it's like 25 millimeter square equals 25 times 10 to the negative 6 meters squared. Right? So it's 25 times 10 to the negative 6, and then times the sine pi over 5 squared, whatever that is, and then divided by the L. Yeah, that's the beauty of it. Everything's in meter. L is meter. L is 5 meter. That's fine. Okay, long story short, you plug everything in and then you do the calculation. Finally, what you're gonna get is a number that is 0.1617. And then remember, because we did everything in meter, it should be meter. And that's your delta. And then we're done, okay? So basically this is like 10 meter long steel beam hanging on the thread. You put this much force on it, you deflect about 16 centimeters, kind of like that, in the middle. Oh yeah, maybe more like that. So yeah, looks like pretty legit. At least you don't have like something like 500 meter or something, or like 0.00001 meter or something like that. So this is how you do it in a real scenario. Okay, I'll assign some homework and just watch for announcement. Okay.